I guess we'll go ahead and get started here. You made it to Thursday afternoon. Congratulations. Glad to see this many people after all the vendor parties last night making it to sessions. Today we're going to talk about a very narrow topic, and I'm kind of glad to see this many people in the room for something as narrow as column store indexing. I'm going to try to make it as interesting as possible by having a decent amount of demos. And we're going to dive into column store indexing, not only for SQL Server 2012 and what non-clustered column stores look like in 2012, but we're going to take a fairly extensive look at clustered column store indexes in SQL 2014. And we'll look at the differences between the two, and we have more than enough time to take questions if there's anything that I'm talking about that's unclear, so feel free to raise your hand and we'll talk. If it gets out of hand, of course, I'll just ask you to defer to the end. But this is a fairly narrow topic, and if we spend an hour and 15 minutes talking on it, I'll be surprised. So we're going to go ahead and get started. My name is Brian Mitchell. This is a little bit about me and where I come from. Most importantly, my Facebook big data research shows that 68% of Brians out there are with an I. And what I want to know is why every time I go to Starbucks, people always assume that it's with a Y. I don't understand that. So I'm trying to start an avalanche of people, trying to assume that it's with an I anyway. So what we're going to talk about is column store indexing. Why is that important to us? Well, there's a few reasons. Everybody's data is growing, and big data, medium data, small data, doesn't really matter. Everybody has constraints on the amount of space and the amount of resources from a physical resources standpoint that they have. And anything that we can do to improve the performance of your existing resources or any resources you're planning on buying is really, it can be a game changer. And clustered column store indexes in a data warehousing workload is definitely a game changer. So you have some needs out there that you have, like hyper-efficient storage subsystems. So you need to be able to have storage that is responsive and quick. And anything that you can do to maximize the amount of space that you use on it most efficiently is really effective. It makes you much more effective at interfacing with your SAN administrators and your organization, and we'll talk a little bit about that. Interactive query response time, so reporting for data warehousing. Our users have gotten to the point where they're no longer near as patient as they used to be about how quickly reports should come up. I think Google and Bing have given our customers unrealistic expectations about how quickly queries will come up in no matter how large the data set, right? So those of us working in corporate environments, our customers are no longer willing to wait X number of seconds. They want things to be quicker. So being able to speed up the query of reporting for a data warehousing workload is always advantageous. But on the other hand, we have this problem of we no longer can just do batch updates at night or on the weekend like we used to. Our users are continually asking for more real-ish time data. So anything that we can do to implement more real-ish time data for them is very helpful for us and for the business at large. And then finally, we have to make it simple. It can't be something where you have to apply a function and then a schema and all that kind of stuff to get to something that you just want something like column store indexing to be really easy to use and to manage, and we'll talk about that. Ideally, cluster column store indexes advance all those challenges. So let's talk a little more detail about the agenda. We're going to talk about some of the design principles behind it. We're going to jump right into demos in like slide 5. And then we'll talk about some column store indexing and batch modes and how we go about speeding up those queries. We'll talk about some of the SQL 2014 improvements in batch processing specifically, and how we go. And then finally, we'll follow up with some best practices around loading and optimizing database and index design and queries. All right, so what we're trying to do with column store indexing in SQL Server 2014 specifically is, kind of work around these design principles. And these are kind of the use cases that we see out there that we really think we can optimize. And that is, first of all, we're mostly talking about data warehouses where data is written once and then read many times. And so generally speaking, where you want to implement column store indexes is in a data warehousing workload where we kind of have a known workload that we can deal with. That being said, there are organizations out there that are implementing column store indexing in a OLTP environment. We have a white paper up on Microsoft.com for bwin, which is an online gaming company, which implemented column store indexing in an OLTP environment fairly successfully. So if you're interested in that, and what they did there, go look at that white paper. Generally speaking, though, today I'm going to speak mostly about data warehousing workloads. Generally speaking, in kind of a star snowflake schema kind of environment, where we're kind of doing a Kimball methodology of fact tables surrounded by dimension tables. Those are generally what we're seeing out there and what our customers are doing, and that's the workload that we're trying to optimize. The idea is that, generally speaking, in this kind of workload, the data is appended to the fact tables. So you're generally not updating new data or deleting data out of the fact tables too often. You're just appending data as necessary as the inserts come in, where, on the other hand, your dimensions may have random updates around. And then we'll go ahead and actually jump into demos, like I said, because I think if we see it in action first and then talk about it, I think that'll give everybody a good idea of where we're going. All right, so I have non-clustered column store indexes, which were introduced in SQL Server 2012, and I have clustered column store indexes, which are going to be introduced in SQL Server 2014. And I'm going to show you the comparisons of what it looks like if we do our normal clustered indexes and non-clustered indexes from the typical row schema that we've always had, also the non-clustered column store indexes, and then finally the clustered column store indexes. That being said, and the workload I have, which is essentially I've already filled up the cache for all of those. I have 3 different databases: AW, which is the traditional clustered and non-clustered indexes, and then AW NCCI, which is non-clustered column store index, and then AW CCI, which is clustered column store indexes. They're the same exact databases, the same amount of data. The only difference is the indexing scheme for the fact sales table, which has been blown up in these databases to be fairly decent size for a laptop so that we can demo this stuff off. So how I'm going to show it off actually is through a report in which we can change the data source depending on what we want to show. So I can, first of all, we could run the report against the traditional schema, which is a fact sales table surrounded by several different dimension tables to show off the report. If I run this, though, it's going to take 20 minutes. So I'm not going to click on it and then stand here and vamp for 20 minutes because I'm not really good at filling time like that. But I can, we can definitely show that off later if we want to towards the end of the session. So I'm not going to show that off because it does take 20 minutes or so to run. What I will show you, though, is we'll start with the non-clustered column store index, and we'll go ahead and run the report. And remember, the traditional SQL 2008, SQL 2012 with the traditional indexes takes about 20 minutes to run. You can see that ran in just a few seconds. And we can see that that report was able to give us a sum of a total of 101 million rows, which isn't too bad. The downside of non-clustered column store indexes in SQL 2012 is that they are non-updatable. So once you put a non-clustered column store index across the table, you can't update it. And so that's the downside. The upside is it's really, really fast. So in SQL 2012, if you want to have this environment, in order to load some more to that table, generally speaking, you have to drop the non-clustered column store index, load your data, and then recreate the index afterwards. I'm now going to show you what the clustered column store index looks like in SQL 2014. And we'll go ahead and change the connection string. And we'll run the report. And same exact data, same amount of rows, and it comes back very quickly. And that's all impressive and everything, and we have 101 million rows in this one also. The difference between the non-clustered and the clustered column store indexes, well, there's several, but the main one that's actually really exciting is the fact that we can go ahead and update data within the clustered column store index in 2014. So how I'm going to show that off is going back over here to SQL Server, and what I'm going to do is I'm going to have this little script, and it's going to insert data into fact sales from fact reseller sales cache. every 2 seconds. And it's going to insert it's 100 and some thousand rows every couple seconds. And I'm going to go ahead and kick this guy off to start running. And he's inserting data now. Now we can go back to the clustered column store index, and we can start refreshing this report. And the idea here is that we're going to continue to add rows as the data is being inserted into the clustered column store index. And so we can see here we've added several different batches. And what we have down here is, if you look down here, what we're seeing here is every time one of those 2-second batch runs goes, that fills up one of those dark boxes. And so we can see how, if we are running reports, we can see that we can now load our data warehouse with the clustered column store index and continue just running reports and being active at the same time. This is a big game changer for us, and we'll talk about why that is when we start talking about how much space we're saving, how we're doing batch mode processing, and everything else. Does anybody have any questions so far? Okay. Now remember, all that's happening on a report that would take 20 minutes to run if you're using standard indexing. And it's taking just literally several seconds to run now. And in fact, what we can do, while I start talking about the next things, is go ahead and change this. It may not be exactly 20 minutes, it may be 10 minutes, but 10 minutes compared to 3 seconds is a big deal. We'll change it to that, and we'll start running it. And I'll go ahead and switch over, and we'll talk, and we'll see how long that takes to run, and I'll watch it. All right, so how does Columnstore's indexes speed up queries? And we'll talk about some of the architecture. So traditionally, we store data in heaps or B trees so that we have clustered indexes, and which organizes the data for us. And then we have some non-clustered indexes that we add, which are copies of subsets of the data that point back to the clustered indexes, right? So traditionally, that's how we stored data. So we were making many copies of the data to get the efficient results that we're used to in a relational or a dimensional model. With Columnstore storage model, what we're doing is we're changing it so that instead of storing the data by row and pages, we're now storing it by column in lobs that sit on top of pages. So what we're doing is each one of these pages stores data from a single column. And what's nice about that, though, is that we go ahead and compress it. So once you've moved it to a single column, we can much more easily compress data from a column than we can from a row. And the reason why is usually when you're dealing with a column of data, you're dealing with like values. Whether or not it's something like a date column that's an integer, or even a date column that's not an integer, you're going to have a lot of like values in a date column. Same thing if you are dealing with a lot of foreign keys within a fact table, right? So if you have a large fact table with literally hundreds of millions of rows, but you have foreign keys to a product table, you may only have thousands or tens of thousands of products. And so thus, we only have a few different, we're able to compress that really well in a column store indexing. Why is that good? Well, the more you can compress it, the more you can move that data throughout your subsystem really easily. And this is really important, and this is really one of the big game changers. So think about it. If data takes up 100 gigabytes of space traditionally in SQL, on disk, and you're able to column store index compress it, and it takes up significantly less space. Now, as we take that data off a disk and move it into memory, we're taking up significantly less amount of space in memory. And if you're taking up less space in memory, that means you can bring more data into memory than you could before because of the compression. And if you have more data in memory, then you have much more memory or much more data in cache that you're more likely to hit when you run queries from reports. If you have more data in cache when you run queries from reports, reports run faster. That's just a matter of fact. So, and if you can do all of that while minimizing the amount of CPU you use while we talk about batch mode processing, you've now optimized all the hardware you already own. And if you're doing a traditional data warehousing workload, this just helps you out with the hardware you already have. I'll go ahead and take a question. Absolutely. So the question is, if you have your fact table in a column store index, a clustered column store index, and you have your dimension table in a relational, traditional row stored index, can you do a join between the two. Oh. Yes. So the question is, can you put the dimensional table in Hackathon? And I have not tried that, but I believe absolutely I believe so. I don't see any reason why you wouldn't be able to. So this will take, no, actually this uses less memory. So this is not, so the question is, does column store indexing take more memory? And the answer is no. So this is not an in-memory technology. The data, just like today, can reside on disk. It will only be pulled into memory when needed, and then will be cached out of memory as needed, as there's memory pressure. Of course, when it's brought into memory, you will get better performance, but even if it's on disk, you're still getting better performance than you would with traditional row store indexing because there is less data to bring through I/O to bring through into memory. But once it's in memory, it takes less space than traditional methods for a couple reasons, and I'll actually talk about those in just a slide or two. All right, so, and one of the reasons why is each column can be accessed independently. So what that means is, if you look up here on this slide, you're only fetching the columns you're needed. So traditionally with row store indexing, when you do a query, you're bringing back the entire page for that query, which includes all the results for that query. Now, you may have an index that only has certain columns, but that's copies of the data. With cluster column store indexing, we have one copy of the data. All of it is column store indexed. But when you query the data, we only fetch the columns that you query. And this is very helpful in a dimensional model where you have very wide fact tables especially. So oftentimes we have fact tables that are, dozens, if not hundreds of columns wide, and most queries hit 10, 15 of them maybe, if you're lucky. And so what we're doing is we're only querying the columns to bring that data in, which again dramatically decreases the I/O. How we go ahead about storing the data kind of looks like this. So we store it in segments. And so the segments are there, and what we have there across the middle there is you see a row group, which comprises a set of rows. So you have segments that everything's stored, and then within a row group, it comprises a bunch of segments that are equivalent for this set of rows. Each segment is stored in a separate blob that sits on a page in memory or on disk. And the important thing to know here is that a segment is the unit of transfer between disk and memory. So each one of these segments contains about 1 million rows worth of data for that column. And so when we do a query, we're pulling 1 million rows from disk into memory on that segment, assuming that it's fully compressed and was fully populated. And we'll talk about that in a little bit. So what that looks like from a traditional table is, let's just assume that you start off with a traditional heap table that looks like this. How we go about processing a cluster column store index is the first thing we do is we actually break it off into those 1 million row groups. So we're breaking them off into those segments right away so that we have 1 million row groups. And then the next thing we do is we go ahead and vertically partition everything into segments. Once you've vertically partitioned everything into segments, the next thing we do is we go ahead and compress the data and store it on disk. Now when we've done this, the first thing you notice is some segments are compressed more than others. It depends on the cardinality of that particular column. So that's kind of important. So there are going to be some things that are more compressible than others. But the second thing to note is there is no longer a row store copy of your data with a cluster column store index. The only thing left is this highly compressed column store index. And that is, from a storage standpoint, that's really important because we're not keeping copies of data everywhere. We have one copy of the data, it's highly compressed, and it's stored in column store format. This is be specific, this is the exact same X velocity technology that's in Excel for Power Pivot, is in analysis services for tabular mode, and then we also leverage it here in SQL Server, both for non-clustered column store indexes and clustered column store indexes. The next thing that's nice is we can do, when you query the data, we go ahead and do segment elimination. And what that means is that as we query the data, in this particular query, we have this query, we're only querying 3 of the columns in the table. First thing we do is we can just eliminate the other 3 columns we're not using. So we're only bringing in half the data of the table into memory in the first place by the query, but it even goes any farther. Because we also have metadata about each one of the segments, we can quickly eliminate which segments we don't need to bring into memory based on any predicates in the query. So in this particular case, what we can do is we're bringing in a much smaller subset of data into memory. On top of that, it's also highly compressed. So this is very efficient for, this is where we're able to get the speed of these kind of queries. And this guy just came back just a minute ago. I don't think that was quite 20 minutes. That was more like about 8 or 9 minutes. So we're talking about the difference between 8 or 9 minutes and 2 or 3 seconds with the clustered column store index. All right, so the next thing that's really exciting, other than just the compression, is also the improvement of the CPU utilization. And that's through something we call batch mode processing. We had batch mode processing in SQL Server 2012, and with SQL Server 2014, we dramatically improve it by increasing the number of operators that will actually run in batch mode. Who here has used column store indexing at all so far? So we got a few people in here. How many people have had problems with it reverting to row mode while running? So a couple people have had problems with that. So one of the nice things about SQL 2014 is the ability to be much more efficient about staying in batch mode, and I'll actually demo that because it handles more operators now, which also gives you better parallelism and allows you to use the multi-core system that you have today. So as we get more multi-core systems and we want to leverage those, the ability to run in batch mode and deal with the number of sectors that are coming through the query processor, we want to be able to do that in a much more parallel manner, and batch mode allows us to do that. The way it does it is by loading data into memory through what we call vectors, and within those vectors then, what we do is we run a process that has 1,000 rows at a time through the CPU. So normally in traditional row store indexing, you are running a row at a time through the CPU and applying your algorithms to it. With batch mode, what we're able to do is basically run 1,000 rows at a time through a CPU, and it's much more efficient, it's faster, everything fits in cache, and what we're doing there is things like filtering and hash joins and hash aggregations are applied at a group of objects instead of an individual object at any great time. So what we have is, it means that you greatly reduce the amount of CPU you use. And when we say 7 to 40 times, that is fairly typical improvements that you see. So we've already talked about how we can reduce the amount of I/O you use by taking up less disk space, and then you use less memory. And now we're talking about actually using your CPUs more efficiently. And for those of you that are DBAs, those are the 3 canaries in the coal mine, right? And if you can optimize those anytime with the existing resources that you have, then that allows you to spend more time possibly solving business problems as opposed to constantly dealing with the hardware limitations that you might have. All right, so cluster column store indexing improvements on top of that. Some of the things that we have going on with cluster column stores is the ability to update them now. So the ability to update and make them faster is very important to us. So how we go about doing that is on the next slide, but at the end of the day, what you need to know is there's no separate copy of the data. We have one copy of the data, and it's updatable, and we do that through something we call a row store on top of it. So now you can insert, update, and delete data, and eliminates the need for any other indexes. In fact, the other indexes are not supported now. If you change your table to a clustered column store index, there is no need for additional non-clustered indexes. So the way we go about doing that is you can go ahead and create a clustered column store index, and I showed you what happens to your table earlier. It basically creates the clustered column store index and removes the previous row store data that you had. And then you can go ahead and bulk insert data into it. And so if you bulk insert data into it, it is going to go into the data as a clustered or a column store row group. So it's going to go into the table, it's going to get compressed in the million row groups and then inserted. If you have less than 1 million rows, it still gets inserted unless it's less than 100,000. If you want to insert data, then by inserting traditional data, it goes into what we call the delta store. So the delta store is a traditional row store heap sitting with your clustered column store table, and that allows us to insert data into it. And once that row store gets to about 1 million rows, what we'll do is we'll have what we call a tuple mover that runs through and actually takes that data, compresses it, and stores it in the column store indexing. So that allows us, from an end user standpoint, they don't know any of that's going on. All they see is one table. What we're doing underneath the hood is we're handling it by having a Delta store so that we can insert data. How we go about deleting data is within the column store, we just do a soft delete. So we just mark something for deletion, and we will go ahead and remove it whenever we do a rebuild of the index later. You have a question, sir?
Yes. Does that mean that we should only use column store indexes on tables that have more than 1 million rows?
The question is, does that mean we should only use column store indexes on tables with more than 1 million rows? We haven't come out with a best practices or anything like that, yes, but generally speaking, I would say yes, that is true. Generally speaking, and we will, by the time SQL 2014 gets out, we will have probably some sort of white paper that gives the kind of guidance that we get through the RDP program that we're working through with customers today, which is the Rapid Deployment Program, which has replaced the TAP program. The idea there is once we've gone out with customers and actually used it extensively with customers and get some idea of what our best practices, we will have those kind of numbers. It's going to be more than 1 million would be my guess. What that exact number is, I don't know. Maybe it's not a number of rows that we come out with. Maybe it's a size of the table that we come out with. But at some point, we will probably have some sort of guidance around that. But I think it's reasonable to say that if you have less than 1 million rows, a traditional indexing scheme is probably the most appropriate thing. Generally speaking, where you're going to get the most bang for your buck for the column store indexing, or clustered column store indexing especially, is for your really large tables. So your fact tables that are in the gigabytes and gigabytes of size, which is most likely much more than 1 million rows. Yes, sir?
Can you do this as an existing table, or you have to start from scratch and copy the big table and cluster it?
So can you add a clustered column store index to a new table, or an existing table? Absolutely. So every table is really kind of an existing table. So you can, and I actually have a slide that kind of walks through how to go about doing that in just a few minutes. So I'll be happy to talk to that then. One more question.
The biggest problem I've had with it is being able to actually create the index. So I'm running on machines that have 256 gig of RAM on them. I'll have a table that may be 40 or 50 gig, and I go to create a column store index, and I get your messages, but it refuses to build column store indexes. They want to put memory.
And is that on non-clustered column store indexes?
I've got it on, I'm not using this one yet. So
Okay. Okay. Memory is really important. CPU is really important to be able to create it quickly. I don't have any specific guidance for you on that at the moment. But I have run into problems even on my local machine where I've run out of memory or I've throttled on CPU because it is a very CPU intensive process. The more resources you can throw at it, the better. My suggestion for something like a 40 gig table, actually now that I think about it, would be partition it, and then you can create it at each index at the partition level. Would probably be the way I would go about handling. So once you start talking about tables in the 40 or 50 gig or bigger range, partitioning might be something that you can do, where you partition the table by date or what have you, maybe by month, and then switch those out, create the clustered column store indexes or non-clustered column store indexes by partition, and then switch them back in. Would be just a thought off the cuff while we're talking. All right. So deletes are the soft deletes, and then updates are an old journaling technique, which is we soft delete the data within the column store, and then we add a new row within the Delta store, and then convert it as we whenever you do either the tuple mover or do a reorganize or rebuild later on. So what does that mean? When I talk about saving space, let's just take it from this database that I showed you guys just a minute ago and just kind of walk through it one at a time. So starting off with the fact sales table that I had blown up to about 100 million rows, and I did some traditional customer indexing on it. When I created 7 indexes, it's a wide table of like 20 or 30 columns or so. I created 7 indexes, single column indexes on it. So that's fairly typical in a data warehouse workload. That's probably even less indexes than what you see in a lot of other data warehouses. That took up 20 gigabytes of space. If I take that same table and add page compression to it, that reduces it by about half, which is pretty good. If I take that table and get rid of all the indexing, then it's only a 5 gigabyte table. Now, the downside of doing that is I now have no indexes and all the queries take a lot longer, right? So that's not really probably the optimal solution that we might have. The table with no indexing and page compression, I can make it a little smaller. So that's the smallest I can make it with traditional row store format, is a table with no indexing and page compression. So that's not going to be a very performant thing, but that's the smallest I can make it. So a table with a non-clustered column store index. So I have the base table, and I've added a non-clustered column store index on every single column in the table. I'm able to get it to be about 7 gigabytes large. And so that should actually perform pretty well, and that's actually what I showed you with the report just a few minutes ago. But with SQL 2014, I can take that same table and create a clustered column store index on it, and it's less than 2 gigabytes. So that's a space savings of 1/10, or so it's 1/10 the original size of the table with the customary indexing. Yes, sir. So the question is, how do things like unique key and foreign key constraints, how are they handled in a clustered column store? And the answer is that if you have a requirement for those, then the clustered column store index is not right for you. One of the things about clustered column stores is there are no other indexes allowed on the table, and which means that things like unique keys and what have you are not allowed on the table. This is not fairly uncommon in data warehousing environments. We've been dealing with this with PDW for a long time. PDW, which is a data warehousing product that we have as an appliance, doesn't have primary keys and foreign keys either. The way that people handle that is by managing their relationships as they load the data through ETL. And that's fairly typical. To be able to get the performance that you want, sometimes there might be some other work up front like that. So handling keys and uniqueness and stuff like that needs to be handled through the ETL pipeline if you want to use a cluster column store index. So think about this from a perspective of just the space savings on your SAN alone. If today you have a 100 gigabyte database in which you're doing some indexing and what have you, and it's basically centered around a couple large fact tables, what does that really mean from a storage perspective? Today, that probably means really your SAN administrator, when you ask for another 100 gigabytes, he's really thinking that's more like a terabyte in space, right? Because 100 gigabytes is actually, first of all, you have to have some sort of RAID array, so that probably doubles your space right there. You have to have some sort of disaster recovery with RAID array. That just doubled your space again. We're now up to 400 gigabytes. You now have to take backups of the data. How many backups are you going to keep of your database? Somewhere that backups have to be stored, so that's another few hundred gigabytes because you may be keeping a couple of the last couple days, plus the transactional logs, plus maybe a week and a month old and maybe a year old or something like that. And you can see where your SAN administrator, when you say I need 100 gigabytes for a 100 gigabytes database, he really hears 800 gigabytes or a terabyte. So when we start talking about reducing the amount of space by, in this example, for example, by 10x, maybe in a real world environment, you may be able to, because you have some tables that you're not putting in cluster column store indexing, maybe you're reducing it by 1/5, so that you're using 20% or 30% of the space that you used to use. If you're going back to your SAN guy and asking for space, you may be only asking for 30 or 40 gigabytes instead of that 100 gigabytes. What does that give you from if you're a DBA in Power? Well, today, he may be giving you that 100 gigabytes, but giving it to you in a RAID 5 array because he doesn't want to deal, because of all those space concerns. If you're able to significantly reduce the amount of space as a DBA, you may be able to have a better conversation with him about having RAID 1 or RAID 10, which gives you better performance and better reliability, but at the same time, you've reduced space and reduced the requirements to him. It could be a win-win situation for both of you. Also in SQL Server 2014, we've reduced the data type support. So the idea here is that in 2012, there was only certain data types that we supported in a non-clustered column store index. And there was a whole list of things that we didn't support, like, varchar max and unique identifier and those kind of things. So in SQL 2014, we support everything but the varchar max, var binary, XML, and spatial. So and if you think about it, those guys are probably less likely candidates for you to want to put in a column store index anyway, because they're not very compressible, generally speaking. Every single one of those is going to be fairly unique, and so there's not a lot of opportunity to compress them, so there's not a lot of advantage to putting them in a column store index. And we'll talk about some techniques to kind of move those out into dimensional tables anyway. Yes, sir? Yes. So the question is, do these support data types cover both non-clustered and clustered column store indexing? And the answer is yes, it does. All right, so batch mode processing. In 2012, we had some engine limitations that caused queries to run in row mode instead of batch mode. A lot of that's been fixed with new support for things like outer join and union join, for example. And I'll actually show a demo here in a minute of the difference between the two and the kind of performance savings you see from 2012 to 2014. And then global batch aggregation, we really improved global batch aggregation, especially for things with large aggregation output by removing some of the row mode aggregation in batch query plans. And then this is actually really exciting, and that is we also provide archival compression by adding archival compression. What we're able to do is significantly shrink the data even more by 27%, up to 27% by partition. So think about a typical fact table in which you may have 7 years of data, and 95% of the queries are against the last year or two, but they want to keep everything because that's what businesses want to do today, right? So why not be able to take those last 5 years of data from 5 years ago and compress that even more? And what that does is that actually it compresses the data even more. There is a slight performance hit when you want to bring it back, of course, because it's compressed even more. We have to uncompress it as we bring it through. But that allows us to significantly shrink the amount of space you may need to use for a typical fact table. This is in 2014. These are all in batch mode and column store indexing improvements in 2014. All right, so let's look at demo. So the question is, if we have a clustered column store index, what is the need for a non-clustered column store index? So the answer is that you may have a table in which you may need to do, like this gentleman talked about earlier, once you have some requirements for uniqueness, for example. So you want to do a unique key or something like that on a particular column. So in that case, clustered column store index may not be appropriate for you, but you still want to take advantage of non-clustered column store indexes for some of the other columns within that table. So you can create a normal row store table with a clustered index. You can create an index with a unique key over that particular column, and then you can create a non-clustered column store index over the rest of the columns within that table, and then have kind of a hybrid mixed mode, which would be the way to kind of attack that problem there. All right, so what I'm going to show you from a batch mode perspective is I have SQL Server 2012 running on my laptop, and I have SQL 2014 running in a VM on my laptop. So what I'm going to do is show you by running the exact same query against the exact same database in SQL 2012. And basically what we have here is we have the kind of query that typically didn't run so well in SQL 2012 and reverted to row mode by doing a left outer join from a dimensional table out to a large fact table. This is the fact table with about 100 million rows. And we'll go ahead and run that and take a look at the result set. And that should just take a few more seconds to run. All right, so that ran there, and what we can take a look at is the execution plan. And over here, we can see that we had the clustered index scan for DIM reseller, but what we want to look at is the Columnstore index scan for fact sales. And if we take a look at this guy, we'll see that he actually reverted to row mode. And you can see here he actually reverted to row mode. And if you scroll down a little bit, you'll see his estimated CPU cost is 55. Let's remember that number when we actually jump back over to the VM and take a look at the estimated cost for SQL 2014. And then down there you can see that the estimated number of rows is about 101 million. And in fact, if you look at the data set that came back, we'll take a look at that and you'll see that it looks exactly the same when we run it in the VM. So going into the VM, we can, am I still loading data? I guess it quit. I probably ran out of space. I forgot to turn that off. Anyway, we can run the exact same query, joining DIM reseller to fact sales. Make sure that we're getting our actual execution plan. And we'll run that against a clustered Columnstore. Actually, we want to run that against the non-clustered Columnstore indexes, so we're like to like. So I ran that against the non-clustered Columnstore index in SQL 2012. I'm now going to run it against the non-clustered Columnstore index in 2014 with the exact same set of data. And it took about 14 seconds to run on my laptop in SQL 2012 within a VM which has less CPUs available to it because it only has 3 out of my 4 available CPUs, and it has the same amount of memory given to it. You can see it ran in 4 seconds as opposed to 16. And the reason for that, and you'll have to bear with me because Zoom-it does not work within my VM right now. I hope you guys can see that okay. You can see right there, the actual execution mode is batch mode. So the difference between batch mode and row mode is that we're able to take 1,000 rows at a time and run it through the CPU, as opposed to a row at a time. That significantly reduces our CPU costs and speeds up the query. And in this case, it sped up the query by about 4 times. And if you look down there at the estimated CPU cost, you can see it's 5.5 instead of 55. So the same exact query, and we've reduced the CPU costs significantly. Question? So the question is the non-clustered Columnstore index in 2014 going to be rewrite as well, like the clustered Columnstore index? And the answer is no. So the non-clustered Columnstore index will still not be updatable in 2014. Only the clustered Columnstore index is updatable. Did I have a missing index indicator? No, so that's on. Oh, I see what you're saying. Yeah, that's definitely a false positive. So to that point that you're making, though, about the difference between non-clustered Columnstore indexes and when to use them, another place where they may not be exactly appropriate is when you have pinpoint queries, right? So one of the places where, while we're assuming when you're using Columnstore indexing, is that you're doing a lot of table scans and bringing back aggregates of data. And this is pretty typical in a data warehousing workload where you're doing large scans of the data, and we want to be able to bring back sums and amounts of wide ranges of data. If, on the other hand, you're trying to derive reports that need pinpoint queries of, give me all the data back for this customer, for this day, for this time, sometimes a traditional indexing scheme with a B tree is going to outperform a clustered Columnstore index sometimes. Did you have a question, sir?
One of the other problems I've had with batch to row mode conversion, so this is 2012, so it's not clustered Columnstore. The machine that had the most resources, so I had a 16-core, 256 gig of RAM, it reverted to row mode. Machine with half the sum of the sales from the table, and that was it. Ran in batch mode on a machine with half the resources, row mode on a machine with most resources.
So that's one of those kind of things where without being there and being able to look at the performance of the box with you and that kind of stuff, I really have no advice for. And the reason why is there's too many other variables outside of that to kind of identify.
It's the only query running on box. Nobody else is running. Complete shutdown on both of them.
Okay, so I'd be happy to talk with you after the discussion if you want to about the details of how going about that, kind of triaging that. All right, so loading cluster Columnstore indexes and going into SQL 2014, some of the best practices that we'll talk about. So really, the idea is that you just want to create a table as usual. So today, like you do today, go ahead and create a table. And then once you've done that, you can create a cluster Columnstore index, which converts the entire table to Columnstore format. Once you do that, you can go ahead and bulk insert into it, or you can do an insert, update, and delete as needed. If you bulk insert into it, we're basically going to create row groups of 1 million rows at a time as you're inserting the data. And then what we'll get is whatever that last row group is, it's probably not full, but we'll go ahead and convert it anyway into Columnstore, unless it's less than 100,000 rows. If it's less than 100,000 rows, we'll go ahead and leave it in the Delta store. And then once you've added more rows to it, and we'll go ahead, the tuple mover will go ahead and reconvert it. On the other hand, if you do an insert or an update into the data, what we'll do is we'll go ahead and just store the data in the Delta store. Once you get more than 1 million rows, we'll start the tuple mover, start moving that into the Columnstore indexing. Basically, the tuple mover is just a service that runs internally that will run every 5 minutes by default. I saw that word by default, and I started looking for it for the conversion somewhere in the properties of SQL Server. I haven't been able to find it yet, but that's one of the things I was looking for over the weekend in 2014. I've only had access to the 2014 bits for about a week myself, and so I haven't been able to find that yet, but I would like to know where it is, where we can go ahead and change that if we wanted to make it less often or more often as necessary. But the idea is that tuple mover will run every 5 minutes and go ahead and convert, if we have more than 1 million rows in the Delta store, into the Columnstore indexing. Or you can go ahead and explicitly start it by doing an alter index reorganize. So an alter index reorganize will take data out of the Delta store and push it into the column store as needed. If you have data in the column store that has been deleted, then the only way to remove it from the column store is to do an alter table rebuild. So again, the batch sizes, the threshold for the tuple mover is 100,000 rows. So the idea is that we'll move the data. Basically, what it means there is, as we insert data for bulk insert, the batch sizes for the tuple mover is 100,000 rows. In other words, if it's more than 100,000, we'll go ahead and convert it in the column store. If it's less than 100,000, we'll go ahead and keep it in the row store. That means that basically, what happens if you get a bunch of 90K row inserts using bulk insert? This is kind of important to know. It's all going to go into the row store, or the Delta store, forgive me. And then once you have 1 million rows, we'll convert it into the column store. On the other hand, if you do a batch of 120,000 rows, we'll automatically convert that and throw that right into the column store. And so you'll get a bunch of segments of 120,000 rows as opposed to the 1 million rows that is ideal. All you need to do to fix that is just go ahead and rebuild the index when you want to. But it kind of gives you an idea of if you're going to leverage cluster column store indexing, then you really want to have an idea of what are those batch sizes that you're inserting. And if they're going to be less than 100,000 rows, you're probably okay. If they're more than 100,000 rows, you want them to be as close to 1 million as possible, if not greater. So if you're doing a bunch of 150,000 row inserts, you're going to get a bunch of small segments in your indexes. And we've been dealing with clustered column store indexes in PDW for a few months now because it's included in the SQL Server 2012 PDW release. And we've seen this with customers where we've really kind of had to watch out for the sizes of batches and kind of playing around them as appropriate. So, building those cluster column store indexes is pretty fast as long as you have the right amount of CPU and memory. An example is I was building some of the column store indexes on my laptop last night in the VM, and I only had one CPU assigned to the VM, and it was taking forever. By stopping my VM and adding 2 more CPUs to it, something that was taking literally, when I say forever, 30 minutes to do, now was taking 5 minutes to do. It was very bottlenecked on the CPU. It also requires quite a bit of memory. So back to your point, sir, some of the things you can do is maybe adjust your degree of parallelism on the boxes, to work with the segment sizes. You can also adjust the physical memory, which you have 2 boxes that are the same. Sometimes you can increase max server memory or change the request max memory grant percent to 50. Some of the things that you can do for low memory, what we're trying to do there is throttle parallelism so that we can get the column store indexes built as necessary. So optimizing database and index design and some of the best practices. Do you still need non-clustered indexes? So yes, this goes back to your point earlier, sir, about yes, you do if you have constraints or triggers on the table. So if you have constraints you need, you can't create a cluster column store index if you have a B tree that's enforcing it in straight. Instead, what you can do is create a clustered index and then the non-clustered column store index. You just won't be able to update the table. So if no constraints are needed, on the other hand, then go ahead and create the table, add the cluster column store indexes. You don't need to make any other indexes, and then you can insert, update, and delete the data as necessary, and you're going to get fairly consistent and fast performance there. On updating a non-clustered column store, there's a couple things you can do. One, you can disable the index, update the data, and rebuild it, of course. The other thing you can do is partition switching. And if you're not doing a lot of partition switching on your fact tables, this is probably a good time to start. I've been working with PDW for the last 3 years. One of the things I've learned from dealing with large data warehouses is if I create partitions on large tables, it makes me much more agile to deal with the data. A lot of times we have to do lots of updates against the data. It's much faster to do updates against sets of partitions as you switch them out, do an update, and switch them back in than it is to try to do an update against a table that is, well, in PDW, I've had experiences where we're trying to update data on a 20 terabyte table. It's just really untenable to do. On the other hand, if we partition it and we switch it out and we're doing updates against 500 gigabytes at a time, we're much more efficient and can get things done. For the non-clustered column store indexes, another way to do some of the updating is to kind of mimic what the cluster column store index does, which is create a delta table and then do a union all view over the top. So you can load data into your delta table. You have your existing data in your non-cluster column store index in your original table, and then on a daily or weekly basis, drop the non-cluster column store index, load the data in from the delta table, rebuild your non-cluster column store index, and now you have a view over both, and you can do it that way. And that can be an efficient way to kind of deal with needing to be able to do updates so that your users can see the whole set of data, but you leverage the non-cluster column store indexes. Other considerations are that if you do have a cluster column store index, you don't need any other indexes, and you can't make any other indexes. So, what that does for us is that saves a lot of space. Now, let's be clear about that. You only have your data in a cluster column store index. It's all zipped up and compressed, and it's stored that way. There is no need to create extra copies of the data for extra indexing. And that's really important from a space and performance saving of the space. And then, of course, we've already talked about the non-cluster column store indexes. And then, partitioning still works. So again, this is another place where partitioning is pretty important because you can do some really good things with partitioning. And that is aging off old data. Instead of having to drop your non-cluster column store index to remove data, if you have it all partitioned, you can just switch out a partition as necessary. So using partitioning to manage fact tables is actually a very, very efficient way to deal with data. All right, so one of the things that we don't support is we don't support strings in column stores. So one of the things you can do, or we don't support some forms of strings, and even if we do, on the ones that we do, it's really slow. So one of the things that we do recommend is that you factor the strings out to dimensions. And that's just taking a fact table that has some strings in it, like you see there on the left, and just creating a key for it and pushing that data out into a dimensional table. And so that way you can create a column store indexing over your fact table and still have a point to the string when people need access to the whatever may be in that string. It's generally kind of a good data warehousing practice. You'll see Kimball talk about it quite a bit when he talks about moving stuff out of the fact tables, but this is just very efficient so we can go ahead and create the column store indexes over the top. Other considerations for moving to column stores for existing tables. One of the things you have to do is drop your other indexes and constraints first, and then you can create your clustered column store index. If you don't have a maintenance window, the idea is that we'll be able to basically take a view over that fact table and redirect to the existing table, and then we can create a new table, create the clustered column store index, copy all the data over to it, and then make sure that we have them both in sync, and then you can switch over to that view over to the new table as necessary. Best practices for query optimization. So there's a whole list of gotchas and workarounds, and at the end of this deck, there is a link to a FAQ that we have up there around column store indexing. That is a really good resource for pretty much every question you might have about SQL 2012 non-clustered column store indexes. For query optimization, one of the key things is to practice good dimensional design so we can get a good star schema. That way we can leverage the star schema query optimizations in SQL Server that's been around since SQL 2008. And then we do recommend the column stores on the fact tables, and we do recommend integer surrogate keys for joins to the dimension tables, and the reason for this is because of the compression of integers. I've been working with, like I said, with PDW for a while. One of the things that we really strive for is doing surrogate keys, doing integers. It improves the performance of join queries significantly over using other kinds of join keys. And basically, the idea behind the clustered column store is if you create it over a table and you meet all the requirements that you need for it, you can just create it and you're done. And then that way you can actually worry about other things, because you can just write queries against it and the performance is going to come out. You're not going to have to worry too much about hints. You're not going to have to worry about managing those indexes too much, other than sometimes having to rebuild that index if you're doing some deletes out of that fact table. But the reality is if you have a partitioned fact table that you're only loading data into, and you're rarely doing deletes or updates, you would rarely have to do a rebuild of that index. And so what that means is that you would be able to just leave the index in place and continue adding data. That is, generally speaking, not true of a row store standard indexes, where you may have a clustered index and then a bunch of non-clustered indexes. While you may be loading data in order on your clustered index, you still need to rebuild your non-clustered indexes on a fairly regular basis, and you shouldn't have to do that as much with a clustered column store index if you are not deleting or updating data too much. So as we go to a summary, I did want to show some of the DMVs available to take a look at how you could go about managing some of that stuff. So back to my environment, there are several DMVs available to kind of manage your environment. So you can take a look at sys.columnstore dictionaries, which will allow you to see the dictionaries of the different indexes that you have within your environment. So in this particular case, these are all the segments that I have within one index within my fact sales table within the clustered column store index table that I have, database that I have. And you can, as you scroll through it, you can see how much space each one of these segments takes up on disk. And what you see is you have some large segments from the original build of the table, and then you also have some smaller segments as I was doing those inserts of the data during that demo originally in the beginning. The sys.columnstore row groups. Allows you to see the row groups within here. So this is actually pretty important. So what you can see here is you can see the state description, which is compressed. This means that it's a column store segment. As we scroll down for this particular table, we should see everything is compressed. Interesting. If you see rows that are in open state, that means that they are in the Delta store, and they're accepting data into the open state. So normally when you load data into a column store index like this, you're going to have a partition that is in an open state. And what that means is it's the Delta store that's accepting rows. And what you want to do is watch out for that. But basically what you can do with this row store row groups is, what I'm looking for is to make sure that my total rows in each one of these segments is 1 million rows. And it's the computer million of 1024 by 1024 or whatever. But you can see each one of these is like that, and we only have a couple of them that are, or a few of them that are smaller than that, and these are our smaller segments. So the way that we would go about getting rid of these smaller segments is to rebuild this table as necessary. So we could go ahead and do an alter index rebuild, and that would go ahead and compress the entire cluster column store index back and reduce the number of segments we have probably, or not probably, it would reduce the number of segments from whatever we have now after all those inserts. We have a total of 133 into something less than that, where each one of them is more full. Yes, sir? So how much, it's going to depend on the resources that you have. While I'm showing this, I can go ahead and show you alter index CCI on this fact sales table. This is just running on my VM. That's 100 million rows. We can go ahead and run him while I'm showing you some of the other queries. I will load this particular .SQL up into the website. So when if you want to download the PowerPoint along with the data, you can go ahead and download these queries too. This particular one just shows you all the column store indexes that you have across your database, and tells you, the object name and the type. So whether or not it's clustered column store, or if I went over here to NCCI, non-clustered column store, it's going to tell you the type and also show you the usage stats. So you can see here that for this non-clustered column store, I have 6 user scans since I started it up, which wasn't too long ago. And you can even see the last user scan. So you can see whether or not your non-clustered column store indexes are being used, and take advantage of that. And then finally down here, you can see the size of your column store index by querying that. And you'll see in this case, the size of it is, in this case, is just a little over 2 gigs for this non-clustered column store index. And it's a fairly involved query of just some of your normal sys.indexes and sys.partitions over to column store segments. And I'm just looking for this particular table and its non-clustered column store size. If I go back over here, you can see that this is still running. It takes a few minutes to run, but it's not obnoxious. I think this takes like 5 or 6 minutes to run. Does it take a table lock? So that's a good question. So the question is, does this take a table lock? And the answer is no, it does not. We can go back here where we're querying DIM reseller against fact sales in the same within the same database. And this is the one that took about 16 seconds. You can see the query comes back. This is the non-clustered column store. I did too, to be honest. So the question is, I thought you were creating a cluster column store index. I was in the wrong database. We can go ahead and go over and we can change that to cluster column store. And run that, and we can change this to cluster column store. So we're rebuilding the index on the fact sales table against which we're going to query against. And I would expect this to come back in just a couple seconds. I believe it was 5 or 6 seconds before. And it comes back in 10 seconds. And I think that might be because it was out of cache. So you can query it at the same time that you're rebuilding it. It's an online operation, which is really important. Again, it's one of those core values of your customers are going to want to update data, and we need to be able to manage these indexes without our customers while our customers are still using the environment. All right, so I'm going to go ahead and go back and just sum up what we've been talking about and take a few questions if you want. So key takeaways: faster query processing, clustered column store indexes save space, and then batch mode processing saves CPU time. It's one of those rare situations where it's win-win-win for everybody, as long as the workload that you have is appropriate to what you need. So if you have a workload that is appropriate for clustered column store indexing, you can get faster query processing so your users are happy and the reports run faster. You get to save space so that you can more appropriately take advantage of the resources that you have. And with batch mode processing, you significantly save CPU time so that you can possibly either put more workload on the machine or at least get more workload out of the machine, use the workload that you have without having to upgrade. That's really about all I have. Here's some additional resources for SQL 2012 and some links. And like I told you, there's that Columnstore index fact link, which is pretty important. That gives you all the information you might want around clustered column store or non-clustered column store indexing in 2012. As the CTP for SQL 2014 comes out later this month, watch for that and get a hold of that and start playing with the clustered column store indexes. Some of the track resources. And of course, don't forget to fill out your evals. And I really appreciate your guys' time, unless there's some questions anybody wants to ask. Oh, all right. Thank you, everybody.